Tonight, we're going to talk about something hiding inside the Milky Way. Not hiding in the way that something small is hard to find. Hiding in the way that something vast and dark and everywhere at once is invisible to almost every instrument we have. We are going to talk about black holes. Not the dramatic ones, the merging pairs that ring the fabric of space-time with waves we can detect on Earth. Not the supermassive one at the center of the galaxy that the Event Horizon Telescope photographed in 2022. We are going to talk about the ones we cannot see, the ones scattered through the disk of the Milky Way, the ones our best models say should be there in the tens of millions, and the ones we have actually confirmed. Which number in the dozens? The gap between those two numbers is the subject of tonight. Before we get started, if you love exploring the deep mysteries of our galaxy as much as we do, take a second to subscribe or like the video. It helps this channel reach more curious minds like yours. Now, let's begin. Let's talk about the number first, because the number is the thing that stops you. Current models of stellar evolution suggest that the Milky Way contains somewhere between 10 million and 100 million stellar mass black holes. Most estimates cluster around the higher end of that range. The figure comes from combining what we know about the initial mass function, the distribution of stellar masses when stars are born, with what we know about stellar evolution timescales and the conditions that produce black holes when massive stars die. The logic is relatively straightforward. Stars with masses greater than roughly 25 times the mass of the Sun are expected to end their lives as black holes rather than neutron stars or white dwarfs. The Milky Way has been forming stars for roughly 10 billion years. Over that time, the number of stars that were born massive enough, lived their lives, and collapsed into black holes adds up to a very large number, 100 million black holes, in the galaxy we live in, right now, and we have directly confirmed the existence of, by the most generous count, a few dozen. Most of those were found because they happen to have a companion star orbiting close enough that material from the companion falls onto the black hole and generates bright X-ray emission that we can detect across thousands of light years. Some were detected as pairs merging together and sending gravitational waves through space, and two, found in 2022 and 2023, were detected by a method so new and so different that they represent a qualitatively different class of discovery. But the vast majority, the tens of millions that should be scattered through the spiral arms and the disk of the galaxy, are completely invisible to us. No one expects this to feel comfortable. No one predicts, when they first hear the scale of the stellar mass black hole population that our models require, that the number of confirmed detections would be so small. Absolutely no one anticipates that a century after we identified black holes as physical objects that general relativity predicts must exist, we would have direct evidence for fewer than 100 of them in a galaxy that should contain 100 million. Let's talk about why they are invisible. A black hole by itself, surrounded by empty space, emits nothing. This is the statement that seems obvious, but is worth sitting with carefully. A stellar mass black hole formed from the collapse of a star perhaps 30 times the mass of the Sun is typically 30 to 60 miles in diameter, not 30 to 60 miles wide in the way a large city is wide. 30 to 60 miles in diameter for an object whose mass is 10 to 30 times the mass of the Sun. Every atom of that original star has been compressed into a region of space smaller than a medium-sized county. Across tens of thousands of light years of interstellar space, an object 30 to 60 miles wide that emits no light is effectively invisible. We cannot image it. We cannot detect its radiation, because there is no radiation. We cannot see the curvature it creates in space, unless something conveniently bright is aligned precisely behind it. And the Milky Way does not arrange its contents for our observational convenience. By the end of tonight, we will understand that the Milky Way we live in is not the one we thought we lived in. The visible stars, the bright gas clouds, the spiral arms we can trace in radio wavelengths are the small fraction of what is actually here. The rest, by number if not by mass, is dark, collapsed, and scattered through the galaxy at densities that mean we would need to search for years with the right instruments to find a single one. Tonight we're going to learn how we find them anyway, and what we have found so far says that the dark Milky Way is stranger than the bright one. To understand why black holes are so hard to find, we need to understand what they are and how they form, not in the abstract, but in the specific, because the specifics determine everything about where they end up and why they are so thoroughly invisible. Let's talk about stellar mass black holes and how the galaxy makes them. When a star more massive than roughly 8 times the mass of the Sun exhausts its nuclear fuel, the core collapses. For stars in the 8 to roughly 20 solar mass range, the collapse is halted by the immense pressure of neutrons packed together, and the result is a neutron star, an object roughly 12 miles in diameter containing more mass than the Sun. The outer layers of the star are expelled in a supernova explosion, one of the most energetic events in the known universe. For stars above roughly 20 to 25 solar masses, the situation is different. The collapsing core has too much mass for neutron degeneracy pressure to halt it. The collapse continues past the neutron star threshold through whatever physics governs the transition, and a black hole forms. The outer layers may or may not be expelled. In some cases, what observers see is a brief flash and then silence. The star simply disappears from the sky. This is called a failed supernova, and the first confirmed candidate, a red supergiant in the galaxy NGC 6946, called N6946 BH1, vanished from observations between 2009 and 2015, with only a brief infrared brightening to mark its passage. The mass cut between neutron star and black hole is not perfectly sharp. Observations from LIGO, the Laser Interferometer Gravitational Wave Observatory, have revealed compact objects in the mass range between 2.5 and 5 solar masses, a region sometimes called the mass gap, because theoretical models historically predicted few or no objects there. What those objects are: neutron stars at the upper mass limit, black holes at the lower mass limit, or something else entirely, is an active area of research. Let's think about the spatial distribution of all those black holes, because where they end up matters for why we cannot find them. When a massive star collapses, the supernova explosion that typically accompanies it is not perfectly symmetric. The asymmetry imparts a kick to the resulting compact object, a velocity in a random direction that can be quite large. Neutron stars are observed to have velocities of hundreds of miles per second relative to their birth location. Some neutron stars appear to have received kicks of over 600 miles per second. These natal kicks are large enough to eject neutron stars entirely from the galaxy, and enough to move them far from where they formed in the spiral arms. Black holes from massive stellar collapse may receive smaller natal kicks, partly because they form from more massive progenitors and the kick velocity scales inversely with mass, but they still receive kicks. The distribution of stellar mass black holes across the Milky Way is therefore not the same as the distribution of the massive stars that created them. They have been scattered, some of them very far from their birth locations, and they have been wandering through the galaxy for billions of years since they formed. Let's talk about the 3 categories of black holes and what we think we know about how many of each there are. The first category is stellar mass black holes, the remnants of individual massive stars, masses between roughly 3 and 100 solar masses, though the upper limit from single stellar evolution is uncertain and depends on stellar physics involving radiation pressure and mass loss. Our best estimates, between 10 and 100 million in the Milky Way. The second category is intermediate mass black holes, abbreviated IMBHs, with masses between roughly 100 and 100,000 solar masses. These are theorized to form either from the direct collapse of massive gas clouds in the early universe, from the mergers of stellar mass black holes in dense environments such as globular clusters, or from runaway stellar mergers in young star clusters. Intermediate mass black holes are predicted to exist, but have been remarkably difficult to confirm. A handful of candidates have been identified, mostly in the centers of globular clusters and in the nuclei of dwarf galaxies, but none have been confirmed with the certainty that either stellar mass or supermassive black holes have been established. The third category is the supermassive black hole at the galactic center, Sagittarius A, with a mass of approximately 4 million solar masses, and the evidence for this one is unambiguous. No one expects the inventory to be this incomplete. We have a well-confirmed supermassive black hole at the center, a predicted population of 10 to 100 million stellar mass black holes scattered through the disk, and a middle range of intermediate mass objects that theory requires but observation has so far struggled to confirm. The Milky Way's black hole census is full of gaps that our current instruments have not yet been able to fill. By the end of tonight, we will understand that what we have confirmed is a tiny sample, and that the sample is biased toward the loudest and most cooperative black holes, the ones with companion stars, the ones that merge, the ones in positions where our telescopes happen to be pointed at the right time. On September 14, 2015, at 5:51 in the morning Eastern Time, two detectors separated by roughly 1,800 miles registered a faint ripple in space-time that lasted less than 0.2 of a second. The detectors were the twin LIGO interferometers, one in Livingston, Louisiana, and one in Hanford, Washington. The signal arrived at the Louisiana detector first by 7 milliseconds, consistent with the roughly 1,800-mile separation and a source arriving from a specific direction in the sky. What those detectors recorded was the death spiral of two black holes merging into one. Let's talk about gravitational waves as a detection method for the hidden black hole population, because the LIGO era has transformed our understanding of what black holes exist and where they come from. LIGO, the Laser Interferometer, Gravitational Wave Observatory, uses a technique called interferometry to measure the distortion of space-time. Each detector consists of two arms, each 2.5 miles long, arranged in an L shape. A laser beam is split and sent down each arm, reflected off mirrors at the ends, and then recombined. If the two arms are exactly the same length, the waves cancel and the detector sees nothing. If space-time is being stretched or squeezed differently in the two arms, the path lengths change by a tiny amount, and the interference pattern shifts. The sensitivity required is staggering. The first detection, designated GW1500914, registered a strain of roughly 10 to the power of -21. This means the 2.5-mile arms changed in length by about 1,000th of the diameter of a proton. LIGO detected that. The mirrors it uses are among the most perfectly polished objects ever made by humans, suspended by glass fibers to isolate them from ground vibrations, cooled in some upgrades to reduce thermal noise. The source of GW1500994 was two black holes, one with a mass of approximately 36 solar masses, and one with a mass of approximately 29 solar masses, merging at a distance of roughly 1.3 billion light-years from Earth. The merger produced a single black hole of approximately 62 solar masses. The missing 3 solar masses were converted to gravitational wave energy and radiated outward. At its peak, the gravitational wave power output was roughly 50 times the combined luminosity of all the stars in the observable universe. Tonight, we're going to think about what this means for the black hole population in the Milky Way, because the LIGO and Virgo detections, now numbering in the dozens, have revealed something important about the distribution of black hole masses. Prior to LIGO, stellar mass black hole masses were known only from X-ray binaries, and the confirmed sample ranged from about 5 to about 20 solar masses. There was a gap below 5 solar masses between the heaviest neutron stars and the lightest black holes that theorists found puzzling but attributed to selection effects or limited sample size. LIGO has changed the picture significantly. Several detections have identified black holes in the mass range between 2.5 and 5 solar masses, in the gap that theory suggested should be sparsely populated. Gravitational 90814, detected in 2019, involved a merger between a 23 solar mass black hole and an object of 2.6 solar masses, a compact object squarely in the mass gap. Whether that 2.6 solar mass object was a very heavy neutron star or a very light black hole remains debated. At the other end of the mass range, several LIGO detections have involved black holes considerably more massive than those found in X-ray binaries, with masses of 60, 80, and in one case over 100 solar masses. These are difficult to explain by the direct collapse of single stars under standard stellar evolution models, because massive stars lose substantial mass through stellar winds before collapsing. Alternative explanations include hierarchical mergers, where smaller black holes merge to produce larger ones, or first-generation black holes from low metallicity stars in the early universe, where mass loss was reduced. No one expects the LIGO mass spectrum to look this complex. No one predicts that the gap would contain objects, or that the high end of the mass range would extend to 100 solar masses, or that the detections would reveal a population of black hole pairs not obviously explained by the binary evolution models that had been built up over decades. Absolutely no one anticipates, in the era of X-ray binary black hole astronomy, that the first direct detections of gravitational waves from black hole mergers would require revising stellar evolution models and generate active debate about previously undetected formation channels. Let's talk about what the gravitational wave detections tell us about the number of merging black hole pairs in the universe. The rate of binary black hole mergers inferred from LIGO and Virgo observations is roughly 10 to 100 per cubic gigaparsec per year. Applying that to the volume of the Milky Way, the expected merger rate within our galaxy is extremely low, perhaps 1 per million years or less. Individual galaxies are not efficient merger factories on human timescales, but the total number of binary black hole systems that will eventually merge is constrained by the merger rate. Each merger requires 2 black holes to have formed close enough in a binary system, or to have been brought close together by dynamical processes, and to lose energy to gravitational wave emission over billions of years until they finally coalesce. The systems that will merge in the future are sitting in the galaxy right now, slowly spiraling, completely invisible, waiting for the laws of physics to close the gap between them. For most of the history of black hole astronomy, there was essentially one way to find a stellar mass black hole. The black hole had to be in a binary system with a companion star close enough that the companion's material was being transferred onto the black hole. That transfer process, called accretion, heats the infalling material to temperatures in the millions of degrees, causing it to emit X-rays. And those X-rays, traveling at the speed of light across thousands of light years, could be detected by X-ray telescopes in space. Let's talk about how this detection method works and why it finds only a very specific subset of the population. The first confirmed stellar mass black hole was Cygnus X1, a bright X-ray source in the constellation Cygnus discovered by a rocket-borne detector in 1964. For a decade after its discovery, Cygnus X1 was debated. It was bright in X-rays, variable in a way consistent with accretion onto a compact object, but compact objects at the time meant neutron stars. The mass needed to be determined to distinguish a neutron star from a black hole. By the mid-1970s, mass measurements from the orbital dynamics of Cygnus XE1's companion star, a blue supergiant called HDE 226868, suggested the compact object had a mass of at least 6 solar masses. Since neutron stars cannot exceed roughly 3 solar masses, Cygnus X1 became the first system for which the black hole interpretation was not just possible, but required by the data. The debate had lasted a decade. Stephen Hawking and Kip Thorne famously wagered on whether it was a black hole in 1974. In 1990, Hawking conceded. Today, Cygnus X1 is known to harbor a black hole with a mass of approximately 21 solar masses, orbiting a companion star at a distance of about 6,000 light-years. The system has been studied in extraordinary detail, but its detection required a specific set of coincidences: a massive companion star actively transferring material, an orbital geometry that allows the compact object's mass to be determined, and a direction that faced Earth at a useful time. Let's think about the selection effects in X-ray binary searches, because they explain why we have found so few black holes. For a black hole to be detectable via X-ray accretion, it needs a companion that is actively transferring mass. In persistent X-ray binaries, the companion star is usually a massive, luminous star with a strong stellar wind, and the black hole continuously accretes wind material. These are relatively easy to find once you build an X-ray telescope. In transient X-ray binaries, the companion is a lower mass star, and the transfer is unstable. Material accumulates in an accretion disk, and then undergoes a thermal instability that triggers a dramatic brightening called an outburst. During an outburst, these systems can become among the brightest X-ray sources in the sky. Between outbursts, they are quiet. Some have recurrence times of decades. The transient black hole X-ray binaries are important because they are the more common type, but they are detectable only during outbursts. We have whole-sky X-ray monitors, like the MAXI instrument on the International Space Station, that track X-ray sources continuously and trigger alerts when new transients appear. Since MAXI began operating in 2009, it has detected dozens of X-ray binary outbursts. Some have been confirmed as black hole systems. Most of the known stellar mass black holes in the Milky Way were found this way, but the selection effect is severe. We can only find X-ray binaries that have had an outburst in the era of X-ray astronomy, that are close enough for their outburst to be detectable above background, and that have the right system geometry to allow mass determination. The inferred population of transient X-ray binaries in the Milky Way is thought to be in the range of thousands of systems. We have found roughly 50 confirmed black hole X-ray binaries. The rest are either quiescent or not yet discovered or not observable from our vantage point. Let's talk about what the confirmed sample actually tells us about the hidden population. From the mass function of confirmed black holes in X-ray binaries, we can see that stellar mass black holes in these systems range from roughly 5 to 20 solar masses, with a few outliers. That range is consistent with stellar evolution models for the progenitor masses that produce black holes rather than neutron stars. The orbital periods range from hours to weeks, reflecting the variety of companion star types and binary separations. What we cannot infer from this sample is the distribution of isolated black holes, the ones that formed in binaries, but then received natal kicks large enough to unbind the system, or the ones that formed from solitary stars and have been drifting alone through the galaxy ever since. Those form the invisible majority. They do not accrete. They do not brighten. They move through the galaxy as gravitational ghosts, influencing the motion of nearby stars over time, but leaving no electromagnetic signal for our telescopes to detect. No one expects the X-ray binary census to reveal the full population. No one predicts that the 50 or so systems we have found in a century of X-ray astronomy represent more than a fraction of a percent of the total. But those 50 systems are what we have, and they are the foundation on which every estimate of the total population rests. The black hole census is inseparable from the neutron star census because the two populations are produced by related processes, are found in many of the same systems, and the boundary between them, the mass gap between the heaviest neutron stars and the lightest black holes, is one of the most observationally active regions of current compact object research. Let's talk about neutron stars in the context of the black hole population, because understanding what neutron stars are and where they are found helps clarify what makes black holes so much harder to detect. Neutron stars are the remnants of less massive stellar collapses, the objects below the black hole mass threshold. They are similar to black holes in many respects. They are dense, compact remnants of stellar death. They can be in binary systems with companion stars, and they can accrete material and produce X-ray emission. But they have one property that makes many of them much easier to find than stellar mass black holes. They can have strong magnetic fields that, combined with rapid rotation, produce beams of radio emission sweeping through space like lighthouse beams. These rotating magnetized neutron stars are called pulsars, and the regularity of their pulsing emission, timed to the rotation period of the star, makes them among the most precisely located objects in the sky. Over 3,000 pulsars have been discovered in the Milky Way, most of them by radio surveys. The total population of pulsars in the galaxy is estimated to be orders of magnitude larger, because most pulsars have beams that do not sweep past Earth, and most have spun down to rotation periods too long to be easily detected by current surveys. The sheer number of known pulsars tells us something about the neutron star census. If we have found 3,000 from only the fraction that beam toward us, the total neutron star population is estimated at roughly 100 million, comparable to the estimated stellar mass black hole population. The two populations together represent the graveyard of the Milky Way's dead massive stars, accumulated over 10 billion years. Let's talk about the neutron star mass limit, because it is central to understanding what falls into the mass gap detected by LIGO. The theoretical maximum mass of a neutron star is determined by the equation of state of dense nuclear matter, the relationship between pressure and density at the extreme densities found inside neutron stars. The exact maximum depends on whether the interior consists of ordinary neutrons or includes more exotic states like quark matter or hyperons. Theoretical calculations give a range from roughly 2 to 3 solar masses for the maximum neutron star mass. Observationally, the highest reliably measured neutron star masses are around 2 solar masses. The pulsar PSR J0740 plus 6620, observed with the NICER X-ray telescope and the Green Bank telescope, has a mass of approximately 2.14 solar masses. The neutron star in the binary pulsar system, J0952-0607, has been measured at approximately 2.35 solar masses, which if confirmed would be the heaviest neutron star known. On the black hole side, the lightest confirmed black holes from X-ray binaries have masses around 5 solar masses. This leaves a gap from roughly 2.5 to 5 solar masses, where neither confirmed neutron stars nor confirmed black holes from X-ray binaries are found. The cause of this gap has been debated for decades. One possibility is that the mass distribution of compact objects genuinely has fewer objects in this range, perhaps because the supernova explosion mechanism preferentially produces either lighter neutron stars or heavier black holes. Another possibility is a selection effect. X-ray binaries in this mass range may have different outburst properties that make them harder to identify as black holes rather than neutron stars. LIGO has now detected several objects in this mass gap. GW190814 involved a merger between a 23 solar mass black hole and a 2.59 solar mass object, the most precisely determined mass gap object identified so far. At 2.59 solar masses, it is either the heaviest neutron star yet found, which would have profound implications for the nuclear equation of state, or the lightest black hole yet found, which would imply the mass gap is narrower than the X-ray binary sample suggested. Let's talk about the population of known X-ray binaries in more detail, because the confirmed sample of black holes in the galaxy is built almost entirely from these systems. As of recent comprehensive catalogues, there are roughly 70 confirmed or strong candidate black hole X-ray binary systems known in the Milky Way and the Magellanic Clouds. The confirmed systems are those with mass function measurements that require a compact object above the neutron star mass limit. The strong candidates are systems with spectral and timing properties most consistent with black holes, but without definitive mass measurements. Of these 70 systems, most are transient systems that spend most of their time in a quiescent state, detectable only during outbursts. The cadence of outbursts is highly variable. Some systems, like A06200 in the constellation Monoceros, the nearest known stellar mass black hole from the pre-Gaia era, at roughly 3,300 light-years, had its most recent observed outburst in 1975. The system may not outburst again for decades to centuries. The inferred number of quiescent black hole X-ray binaries in the Milky Way, extrapolated from the observed outburst rate and models of binary evolution, is in the range of a few thousand to tens of thousands. These are all systems where the black hole has a companion star, and the companion is currently not transferring much mass. They are quiet, dark, waiting. The overwhelming majority of the 10 to 100 million stellar mass black holes are not in X-ray binary systems at all. They have either no companion, or a companion so widely separated that accretion never occurs. No one expects 70 confirmed systems to represent an adequate sample for characterizing a population of 100 million objects. No one predicts that the X-ray binary catalog would converge on a representative picture of the mass and spin distribution of stellar mass black holes in the Milky Way. The confirmed sample is a tiny, biased, observationally convenient subset of a vast hidden population, and drawing global inferences from it requires caution that the field has not always applied. We will understand that the neutron star and black hole populations together constitute the dense remnant graveyard of the galaxy, a complement to the visible stellar population that is equal in number, distributed similarly through the disk, and almost completely invisible by any of the methods we have developed to study the night sky. In 2022, a team of astronomers announced the discovery of a black hole using a method that had never successfully found one before. It was not detected by X-rays. it was not detected by gravitational waves. It was detected by watching a star wobble. Let's talk about Gaia BH1, because it represents a fundamentally different way of finding the hidden population, and because what it found changes some of our assumptions about where black holes live. The European Space Agency's Gaia spacecraft was launched in 2013 with the mission of mapping the positions, distances and motions of more than 1 billion stars in the Milky Way with extraordinary precision. It is an astrometric mission. It does not take pictures in the conventional sense. It measures where things are, how far away they are, and how they are moving, to levels of accuracy that were not previously achievable. When a star has a companion object that is not visible, the invisible companion still exerts a gravitational tug. As the two objects orbit their shared center of mass, the visible star traces a tiny elliptical path on the sky, relative to more distant background objects. For a black hole companion, the visible star's wobble is the only evidence of what it is orbiting. Gaia BH1 is a solar-type star, slightly cooler and less luminous than the Sun, located approximately 1,560 light-years from Earth, in the constellation Ophiuchus. Gaia's astrometric data showed that this star was not moving through space in a straight line, but was executing a subtle wobble, tracing out a portion of an ellipse over the course of the mission's observations. The period of the wobble is 185 days. The amplitude of the wobble, analyzed carefully, required the invisible companion to have a mass of approximately 9.6 solar masses. Nothing natural other than a black hole accounts for an invisible object with that mass in a compact binary orbit. A neutron star at that mass would exceed the maximum allowed mass by a factor of 3. A white dwarf would require a mass 5 times the Chandrasekhar limit. A cluster of faint stars at that combined mass would be detectable in follow-up observations. None of those follow-up possibilities survived. Gaia BH1 was a black hole. The finding, published in Nature in late 2022, was remarkable for several reasons. At 1,560 light-years, Gaia BH1 is the closest known black hole to Earth. But more importantly, it is a dormant black hole. It is not accreting material from its companion. The companion star is a main sequence star similar to the Sun, not overflowing its gravitational boundary onto the black hole. The system is quiet. Before astrometry, it would have been invisible. Tonight we're going to talk about what happened next, because the discovery of Gaia BH1 prompted immediate searches for more systems using the same method. In 2023, the same team and independent groups identified Gaia BH2, a second dormant black hole detected by the stellar wobble method. Gaia BH2 is located approximately 1,200 light-years from Earth in the constellation Centaurus, making it the second closest known black hole. Its companion is a red giant star with a mass slightly less than the Sun's. The black hole has a mass of approximately 8.9 solar masses. The orbital period is 1,277 days, nearly 3.5 years. Gaia BH2 is notable because its companion is an evolved star. A red giant has expanded compared to its main sequence phase, and the evolutionary stage of the companion can be used to constrain the age of the system. Gaia BH2 appears to be an old system. The red giant companion and the orbital separation suggest the two objects have been in this configuration for billions of years, orbiting each other quietly as the galaxy turned around them. No one expects the Gaia astrometry approach to find these systems in the first years of the mission. No one predicts, when Gaia was being designed and launched, that the initial data releases would yield confirmed black holes by the astrometric wobble of their companions. Absolutely no one anticipates that the two closest black holes to Earth would turn out to be dormant systems invisible to every prior detection method, sitting within 2,000 light-years of us, right in our cosmic neighborhood. Let's talk about what Gaia BH1 and BH2 imply for the number of similar systems in the galaxy. The Gaia mission's sensitivity for astrometric wobble detection is approximately proportional to the brightness of the host star and inversely proportional to the distance. Gaia BH1 and BH2 are relatively nearby systems with bright enough companions to make them detectable within Gaia's current data releases. But the survey covers the whole sky. If two dormant black hole systems exist within roughly 1,500 light-years, and if those two systems were found in the earliest and noisiest data releases, the population of similar systems within a few thousand light-years is probably much larger. Statistical extrapolations from Gaia BH1 and BH2, combined with models of binary star evolution, suggest that the number of Sun-like stars with dormant black hole companions in the Milky Way is in the tens of thousands, and possibly higher. This is a population entirely distinct from the X-ray binary black holes. It is a population of quiet, dark, ordinary-looking companions that have been orbiting their stars for billions of years, with no indication that anything unusual is happening. By the end of tonight, we will understand that Gaia BH1 and BH2 are not just two data points. They are the first confirmed members of a population we have been unable to detect for a century of black hole astronomy. The question of how many black holes the Milky Way contains reduces, at the most fundamental level, to a question about stellar evolution. Which stars become black holes? Which stars become neutron stars? And which stars produce white dwarfs and planetary nebulae? The answer to that question, integrated over the 10 billion-year history of star formation in the Milky Way, gives us the total population. And the answer is more complicated and more interesting than the simple mass threshold that is often cited. Let's talk about what we actually know about the stellar mass cutoff for black hole formation. The classical picture says that stars above roughly 25 solar masses produce black holes. Stars between roughly 8 and 25 solar masses produce neutron stars. Stars below 8 solar masses produce white dwarfs. This picture is approximately right, but significantly oversimplified, and the deviations from it are important for understanding the black hole census. The first complication is stellar metallicity. Stars with more metals, astronomical shorthand for all elements heavier than helium, lose more mass during their main sequence lives through radiation-driven stellar winds. A massive star in the present-day Milky Way, which has been enriched by billions of years of stellar nucleosynthesis, might start at 60 solar masses and lose 40 solar masses to winds before it dies. The remnant is a star that was originally very massive, but by the end of its life is not quite massive enough to produce a very massive black hole. In contrast, stars in the early universe, formed from gas that had not yet been enriched by supernovae, retained much more of their mass. The most massive population, the 3 stars, the first stars, may have produced black holes with masses in the tens to hundreds of solar masses directly from their collapse, because there was no wind-driven mass loss to drain them. This explains, at least partially, why some LIGO detections show black holes with masses in the 50 to 100 solar mass range that are difficult to produce from present-day stellar evolution models. They may be the remnants of stars that formed early, in low metallicity environments, or through channels not well represented in our nearby stellar sample. Let's talk about the mass gap at the upper end, because it produces a category of black holes that cannot form through ordinary stellar collapse. Between roughly 50 and 130 solar masses at the pre-supernova stage, a process called pair instability affects the stellar core. As the temperature in the core reaches billions of degrees, energetic photons begin to spontaneously produce electron-positron pairs. The energy that was providing pressure support is diverted into pair creation. The core contracts rapidly, and explosive nuclear burning is triggered. The entire star is disrupted. Nothing is left. No black hole, no neutron star. The massive star is completely destroyed in what is called a pair instability supernova. Stars above roughly 130 solar masses at the pre-supernova stage avoid this fate in a different way. They are so massive that the explosive burning is not enough to disrupt the entire star. The outer layers are expelled, but the core collapses directly into a massive black hole, producing what is called a pair instability pulsational supernova, followed by collapse, or in extreme cases, direct collapse with minimal mass loss. This creates what theorists call the pair instability gap in the black hole mass function. No black holes between roughly 50 and 130 solar masses can be formed by direct stellar collapse of present-day stars. They can, however, be formed by the merger of smaller black holes. When two black holes merge and produce a remnant in this mass range, that remnant is a second-generation black hole, a black hole made from black holes rather than from stars. Several LIGO detections appear to involve black holes in or near this mass gap. GW1990521, a merger detected in 2019, involved a black hole of approximately 85 solar masses in the final state, requiring at least one of the merging objects to be in the forbidden mass range. The interpretation that one or both objects were already second-generation mergers has significant implications for the environments where black holes can merge multiple times, which points to the dense cores of globular clusters or nuclear star clusters rather than ordinary field binaries. Let's talk about failed supernovae more specifically, because they represent a direct formation channel for massive black holes without the supernova signal we normally associate with their creation. When a very massive star collapses and the core has too much angular momentum or mass to form a stable neutron star, the collapse proceeds past the neutron star density directly to a black hole. The outer envelope may receive only a very weak shockwave, not enough to produce a bright supernova. The star may simply disappear, with only a brief infrared brightening from the redistribution of energy in the envelope. The candidate event N6946BH1 occurred in the spiral galaxy NGC 6946, sometimes called the Fireworks Galaxy, because it has hosted 10 observed supernovae in the past century. In 2009, astronomers identified a red supergiant at a position in NGC 6946 and tracked it across multiple years. The star brightened in the infrared during 2009, then faded. By 2015, it had essentially vanished from the position where it had been observed. Hubble Space Telescope imaging of the region showed no source at that location, with properties consistent with the original red supergiant. The most natural interpretation is that N6946BH1 underwent a failed supernova, collapsing directly to a black hole with insufficient ejected energy to produce a visible explosion. The estimated mass of the progenitor was approximately 25 solar masses, right at the threshold where theory predicts the failed supernova channel becomes relevant. No one expects the fraction of massive stars that die as failed supernova to be small. No one predicts, based on the theoretical models that became available in the 2010s, that only a negligible fraction of collapses fail to produce bright supernovae. Current models suggest that between 10 and 40% of core collapses in massive stars may be failed supernovae. If accurate, this means that a significant fraction of the Milky Way's stellar mass black holes formed not with the spectacular explosion of a supernova, but with only a brief flash and then silence. Many of them may also have received smaller natal kicks, because the asymmetric mass ejection that produces kicks in ordinary supernovae is absent, and they may therefore be more concentrated toward the galactic disk, where they formed rather than scattered widely. We will understand that the diversity of pathways by which stars become black holes contributes directly to the diversity of the hidden black hole population. Some received large kicks. Some received small ones. Some formed in the early universe from pristine gas. Some formed through mergers of smaller black holes. The single number, 100 million, conceals a population with enormous internal variety in mass, spin, velocity, and formation history. There is a third method for detecting isolated black holes, one that does not require them to have a companion star, does not require them to be accreting, and does not require them to be merging with anything. It only requires them to pass in front of a background star at approximately the right distance. Let's talk about gravitational microlensing, because it offers the most direct path to finding the truly isolated black holes, the ones drifting alone through the galaxy with no companion and no ongoing process to make them bright. Gravitational lensing is a consequence of general relativity. Any massive object bends the path of light passing near it. When a massive object passes directly in front of a more distant background star as seen from Earth, the bending of light can focus and amplify the background star's brightness. For objects as small as stellar mass black holes, the angular separation of the multiple images created by the lensing is too small to be resolved, but the total brightness of the background star still increases, rises to a peak, and then falls as the lensing object continues its motion across the line of sight. This is called a microlensing event. The signature of a microlensing event is a characteristic light curve, symmetric in time, achromatic, meaning the brightening is the same at all wavelengths, and non-repeating. The peak brightness, the timescale of the event, and the asymmetries in the light curve when the lensing object is close to the center of the line of sight all encode information about the lensing object's mass and distance. The optical gravitational lensing experiment, OGLE, run by the University of Warsaw, has been monitoring the brightness of millions of stars toward the galactic bulge since 1992. The densely packed stars of the bulge provide a rich source of background targets, and the motions of foreground objects through the disk create a steady trickle of microlensing events. OGLE has detected thousands of microlensing events. Most of these events are caused by ordinary stars. Some are caused by brown dwarfs, stellar remnants like white dwarfs, or neutron stars. A small fraction should be caused by black holes, but distinguishing a black hole lens from a stellar lens requires either knowing the distance and transverse velocity of the lens independently, or detecting a subtle extra effect called astrometric lensing, in which the position of the background star shifts slightly during the event because the lensed image centroids move. Let's talk about a specific event, because in 2022, a microlensing detection was claimed to be the first isolated black hole identified. The event, designated MOA 2011 BLG 191 or OGL 2011 BLG 0462, was a long-duration microlensing event observed in 2011 with both ground-based photometric observations and the Hubble Space Telescope's astrometric capabilities. Long-duration events are more likely to be caused by massive lenses, because more massive objects produce longer timescale brightening signatures. The Hubble astrometric measurements tracked the shift in position of the background star over years following the event, providing the additional information needed to break the degeneracy between lens mass, distance, and velocity. Two independent analysis teams working from the same Hubble data both concluded that the lens was a compact object but differed on the exact mass estimate One team reported a mass of roughly 7 solar masses, well above the neutron star limit, and therefore a black hole. The other team reported a mass in the range of 1.6 to 4.4 solar masses, straddling the mass gap between neutron stars and black holes, and leaving the classification ambiguous. No one expects the first isolated compact object detection via microlensing to yield a clean answer. No one predicts that the team best positioned to resolve the ambiguity would find themselves in disagreement about the mass of their own detection. The uncertainty reflects the genuine difficulty of extracting precise masses from astrometric measurements of stars thousands of light years away, where the shifts involved are measured in microarc seconds. Let's talk about what the microlensing approach can ultimately contribute to the black hole census. If the Milky Way contains 100 million stellar mass black holes distributed through the disk, a significant fraction of them will occasionally pass in front of background stars in the bulge as seen from Earth. The expected microlensing rate from black holes alone is calculable given the assumed population. Current models suggest that roughly 1% of all microlensing events toward the galactic bulge are caused by black holes. With OGLE detecting thousands of events over its history, that implies several dozen black hole microlensing events have already occurred in the data. The challenge is extraction. Most of those events look similar to events caused by stellar mass lenses. To distinguish them, you need the long-duration events, and within those, you need either astrometric measurements from space or careful parallax measurements that use the Earth's orbital motion to encode additional information about the lens geometry. The Nancy Grace Roman Space Telescope, formerly the Wide Field Infrared Survey Telescope, approved by NASA and planned for launch in the mid-2020s, has a specific microlensing program as one of its core science objectives. It will monitor more than 100 million stars in the galactic bulge with a time resolution and sensitivity far exceeding any ground-based survey. Its astrometric capabilities will allow it to detect the subtle positional shifts from microlensing events and, critically, to distinguish black hole lenses from stellar lenses with sufficient statistical power to begin building a real catalogue of isolated black holes. The Roman Space Telescope's microlensing survey is expected to detect between tens and hundreds of isolated black holes, depending on the assumptions about their mass and velocity distribution. That would be a transformational sample, and it would be entirely composed of isolated black holes that no other method could have found. By the end of tonight, we will understand that the path to filling in the black hole census runs through multiple independent detection methods, each accessing a different slice of the hidden population, and that we are at the beginning of an era in which the number of confirmed black holes in the Milky Way may grow from the dozens to the thousands within a decade. The black holes we have been discussing so far are all the remnants of stars. They formed when massive stars died, and they carry in their masses and spins the imprint of the stellar progenitor that created them. But there is a theorized category of black holes that predates the first stars, a category that could in principle account for a significant fraction of the universe's dark matter, and whose detection is the subject of one of the most active debates in modern cosmology. Let's talk about primordial black holes, because they add a layer to the hidden black hole problem that goes beyond stellar evolution entirely. In 1971, Stephen Hawking and Bernard Carr proposed that black holes could have formed in the very early universe, in the first fractions of a second after the Big Bang, from density fluctuations in the hot, dense plasma that filled space. Regions where the density was slightly above average would have had enough pressure to collapse under their own gravity before pressure waves could stabilize them, creating black holes with masses determined by the cosmological horizon size at the moment of collapse. These primordial black holes would have formed before any stars, and they would carry no record of stellar evolution in their properties. The mass range of primordial black holes, if they exist, is extraordinarily broad. Depending on when during the early universe they formed, their masses could range from subatomic, smaller than an atomic nucleus, to millions of solar masses. The constraints on their existence come from a variety of observations, each ruling out different parts of the mass spectrum. Very low-mass primordial black holes, those with masses below roughly 10 to the power of 15 grams, a few times the mass of a mountain compressed to the scale of a proton, would have already evaporated through Hawking radiation over the age of the universe. Their evaporation would have produced a gamma-ray background detectable by gamma-ray telescopes, and the constraints from gamma-ray background measurements rule out primordial black holes in this mass range as significant contributors to dark matter. Higher mass primordial black holes, in the range of roughly 1 to 1,000 solar masses, have been constrained by a combination of microlensing observations, gravitational wave constraints from LIGO, and observations of the cosmic microwave background. Early microlensing surveys, including MACO and EROS, searched for compact dark objects in the halo of the Milky Way by monitoring stars in the Magellanic Clouds. Their non-detection of microlensing events constrained the fraction of the dark matter that could be in compact objects in a specific mass range. The constraint from EROS was particularly powerful. Compact dark objects in the mass range of roughly 0.1 to 10 solar masses cannot account for more than about 10% of the dark matter in the Milky Way's halo. But a window in the primordial black hole mass range remains less constrained. Masses in the range of roughly 10 to 1,000 solar masses are partially constrained by LIGO observations, because if this mass range were abundant, we would expect to see many more gravitational wave detections than we do. But the constraints are not yet tight enough to rule out primordial black holes as a meaningful component of dark matter in this mass range. And LIGO itself has detected mergers involving black holes that are difficult to explain by stellar evolution models, raising the question of whether some of the merging objects could be primordial. Let's talk about intermediate mass black holes, because they represent the least observationally established category and the one whose existence or non-existence is most important for understanding how galaxies built their central supermassive black holes. Intermediate mass black holes, with masses between roughly 100 and 100,000 solar masses, are predicted by multiple formation channels, but have proven remarkably difficult to confirm. The formation channels include the direct collapse of massive gas clouds in the early universe without first forming stars, the runaway merging of massive stars in young, dense star clusters, and the hierarchical merging of stellar mass black holes in the cores of globular clusters over billions of years. If intermediate mass black holes form in globular clusters and then sink to the centers of those clusters through dynamical friction, they might be detectable by the kinematic signatures they imprint on the stellar velocity dispersion. Stars near the center of the cluster moving faster than would be expected from the stellar mass alone. Several searches have been conducted using this method, and several candidates have been identified, but none has achieved the level of confirmation of either stellar mass or supermassive black holes. The kinematic signatures are subtle and can be mimicked by concentrated populations of stellar remnants, making unambiguous identification difficult. A candidate intermediate mass black hole in the dwarf galaxy, Hennes 2 to 10, was announced in 2011 and supported by X-ray and radio observations consistent with active accretion onto a compact object of mass, roughly 1 million solar masses, which places it at the lower end of the supermassive, rather than the intermediate mass range. More recently, the Hubble Space Telescope found evidence for an intermediate mass black hole candidate in the globular cluster NGC 6397, using the kinematic signatures of the stars in the cluster's core. No one expects the intermediate mass black hole census to be this sparse given how strongly theory predicts their existence. No one predicts that the mass range between stellar and supermassive would be so poorly observationally sampled. Absolutely no one anticipates that the gap in our knowledge between black holes we can confirm via X-ray binaries and gravitational waves on one side, and the confirmed supermassive black holes at galactic centers on the other, would remain this wide after decades of targeted searches. Let's talk about why filling the intermediate mass gap matters for cosmology. Supermassive black holes, like SGAI, in our own galaxy with 4 million solar masses, are present at the centers of most large galaxies. How they got so massive is a fundamental open question in astrophysics. They must have started as smaller black holes and grown, either by accreting gas over cosmic time, by merging with other black holes, or by some combination. But the seeds of those supermassive black holes, the initial objects that began to grow, are not established observationally. They might have been stellar mass black holes that grew slowly over billions of years. They might have been intermediate mass black holes formed by direct collapse of massive gas clouds in the early universe, providing a larger starting point. Or they might have been something else entirely, exotic objects in the very early universe for which we do not yet have a clear theoretical picture. We will understand that the black hole population of the Milky Way and the universe is a nested set of mysteries. The stellar mass ones are real but uncounted. The intermediate mass ones are predicted but unconfirmed. And the question of how the supermassive ones grew to their current sizes from whatever seeds they began, as connects the physics of the very early universe to the observed universe we live in today. Everything we have discussed so far has been about the stellar mass black holes scattered through the disk of the galaxy. But the Milky Way also contains a black hole of a categorically different scale at its very center, and the story of how we found it and what it has taught us about the black hole content of galaxies is worth sitting with carefully. Let's talk about Sagittarius AI and what it tells us about the dark heart of the Milky Way. The galactic center is not a quiet place. It is one of the most energetically dense regions in the Milky Way, full of hot gas, massive young stars, supernova remnants, and a complex of radio emission sources that radio astronomers have been studying since the 1950s. In 1974, astronomers Bruce Ballack and Robert Brown, using the National Radio Astronomy Observatory's interferometer, detected a bright, compact radio source right at the dynamical center of the galaxy. They named it Sagittarius A, the asterisk indicating the brightness and activity of the source, in the same notation used for excited atomic states. For the following 2 decades, astronomers debated what Sagittarius A was. A massive black hole was the most natural explanation, but proving it required measuring the motions of stars close enough to the center that they would be significantly affected by whatever compact mass was there. In the 1990s, 2 independent groups began this work. Andrea Ghez at the University of California, Los Angeles, used the Keck telescopes in Hawaii with adaptive optic systems that partially corrected for the blurring effect of Earth's atmosphere. Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics used the Very Large Telescope Array in Chile. both groups began tracking the precise positions of individual stars near the galactic center, mapping their movements over years and then decades. What they found was extraordinary. The stars were orbiting at extraordinary velocities. One star, designated S2 by Genzel's team and S0-2 by Gez's team, was found to have an orbital period of approximately 16 years, moving at speeds of up to 3% of the speed of light at its closest approach to the center. The full orbit, traced over 2 complete cycles from the early 1990s to the 2010s, was a textbook ellipse, and the object it orbited was confined to a region smaller than our solar system, with a mass of approximately 4 million times the mass of the Sun. No known configuration of normal stars, neutron stars, or any other visible matter could produce that combination of mass and compactness. The only known physics that could account for it was a supermassive black hole. In 2020, the Nobel Prize in Physics was awarded to Roger Penrose, Reinhard Genzel, and Andrea Ghez. Penrose for the theoretical framework establishing that black holes are a prediction of general relativity. Genzel and Ghez for the stellar orbit observations that established the presence of a supermassive compact object at the center of the Milky Way. Tonight, we're going to talk about what happened in April 2022, because it added a visual dimension to what had previously been purely a dynamical measurement. The Event Horizon Telescope is not a single telescope. It is a global network of radio dishes spread across multiple continents, linked together to function as a single Earth-sized aperture, using a technique called very long baseline interferometry. Its resolution is sufficient to image the immediate surroundings of a supermassive black hole at the distance of the galactic center. On May 12, 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A. The image showed a bright ring of hot plasma, millimeter wavelength radio emission from gas orbiting the black hole, surrounding a dark central region, the shadow of the event horizon, roughly the size predicted by the mass determination from stellar orbits. The image confirmed visually that the object at the center of the Milky Way is a black hole in the specific theoretical sense, a region of space-time from which nothing can escape. The image of Sagittarius AI was technically far more challenging than the collaboration's earlier image of the supermassive black hole in the galaxy M87, released in 2019. M87 is 6.5 billion solar masses, far larger and more slowly varying than Sagittarius A, which changes on timescales of minutes as gas swirls and turbulence evolves in the accretion flow. Capturing SGR-AA required combining thousands of images taken over multiple nights to average out the variability. Let's talk about what SGR-AR's activity, or lack of it, tells us about the environment around the galactic center black hole. SGR-I is remarkable for how quiet it is. Relative to the supermassive black holes in other galaxies, many of which are active galactic nuclei with jets, bright emission across multiple wavelengths, and accretion rates that make them visible across the observable universe. SGR-AI is essentially dormant. It flares occasionally in X-rays and infrared wavelengths, brightenings lasting tens of minutes associated with gas clumps crossing the innermost stable orbit. But it does not have a persistent jet. It is not a quasar. Its accretion rate is among the lowest measured for any supermassive black hole. No one expects the central black hole of a spiral galaxy to be this quiet. No one predicts, in the early era of active galactic nucleus research, when quasars were being discovered at cosmological distances, that the black hole at the center of our own galaxy would be so inactive as to require decades of careful observation to confirm. the Milky Way's central black hole appears to be in a quiescent state, perhaps because the fuel supply of gas and dust has been depleted by previous episodes of activity, or perhaps because the dynamics of the galactic center region simply do not efficiently funnel gas inward at the rates that power the most luminous quasars. By the end of tonight, we will understand that even the black holes we know about are stranger and more varied than simple categorizations suggest, and the ones we do not know about, the tens of millions of stellar mass black holes drifting through the disk, are stranger still, because we have so little information about what they actually do with their time. The center of the Milky Way is not a place we can visit or even observe easily. It is hidden behind roughly 25,000 light-years of interstellar gas and dust that absorbs visible light so completely that optical telescopes see nothing in that direction. What we know about the galactic center has been learned through radio waves, which pass through the dust unimpeded, infrared light, which penetrates the dust partially, and X-rays, which come from the hottest and most energetic processes. What those observations have revealed is that the region within a few hundred light-years of SGR-A2 is one of the most densely populated and energetically intense environments in the Milky Way, and it is also, according to theoretical predictions that have been difficult to verify observationally, one of the places most densely populated with stellar mass black holes. Let's talk about the galactic center stellar population and what it implies for the black hole distribution. The innermost parsec, roughly 3 light-years, around SGR-A is home to a young cluster of massive stars called the S-star cluster, including the star S2, whose orbit provided the key evidence for the supermassive black hole's mass. These stars formed within a few million years ago, which raises an immediate puzzle, because the tidal forces from SGR-A at that distance should have torn apart any molecular cloud before it could collapse to form stars. How these young, massive stars came to be so close to the black hole is still debated. One hypothesis is that they formed in a disk of gas that fell into the galactic center after a major gas infall event. Another is that they formed further out in a massive cluster that was drawn inward by dynamical friction. The puzzle is called the paradox of youth. Beyond the S-star cluster, out to distances of roughly 30 to 100 light-years from the center, there is a dense nuclear star cluster, one of the most massive star clusters in the galaxy, with a total mass of roughly 25 million solar masses. This cluster is the product of billions of years of star formation events and the accumulation of stars in spiral from the outer galaxy. It contains stars of all ages, from young massive stars formed in recent events to old low-mass stars that have been there for billions of years. The older massive stars in this population have long since died. They became supernovae and black holes. Those black holes, unlike the ones scattered through the general galactic disk, did not receive large natal kicks that would have ejected them from the strong gravitational potential of the galactic center. They are still there. The nuclear star cluster should be substantially enriched in black holes compared to the field. Let's talk about the dark cusp, because it is one of the most striking predictions of galactic center black hole theory, and one of the least observationally confirmed. Theoretical models of how stellar mass black holes behave near a supermassive black hole predict that they will concentrate in a centrally enhanced distribution called a dark cusp. The physics is energy equipartition in a dense stellar environment. Black holes are more massive than the average star. In a process called dynamical friction, more massive objects lose energy to the surrounding lighter mass stellar population and sink toward the center. Over billions of years, the 10 to 30 solar mass black holes in the nuclear star cluster should have preferentially sunk toward SGR-A, creating a centrally concentrated population. The predicted density of stellar mass black holes within a parsec of SAGRA is extraordinary. Some models suggest thousands to tens of thousands of black holes within a few light years of the supermassive black hole. If the dark cusp exists as predicted, the nuclear star cluster core is the densest concentration of black holes in the galaxy. Direct observational confirmation of the dark cusp has been elusive. In 2018, a team using Chandra X-ray observatory data reported finding 12 accreting compact objects, possibly black holes, within 3 light years of SAGRAI. By detecting their X-ray emission when they briefly accreted gas from a companion or from the dense interstellar medium. This is consistent with the dark cusp prediction, but represents only the accreting tip of a much larger population. No one expects the dark cusp to be easy to detect directly. No one predicts that the black holes preferentially concentrated at the galactic center would be easily identified, because most are not accreting and therefore not producing electromagnetic signals. Their gravitational effects on stellar orbits might reveal them in aggregate, but individually they are as invisible as their counterparts throughout the rest of the disk. Let's talk about tidal disruption events, because they reveal what happens when the galactic center's stellar compact objects interact with the supermassive black hole in a dramatic way. When a star passes too close to SAGRA, the tidal forces across the star exceed the star's self-gravity and tear it apart. The debris of the disrupted star falls into the black hole over months to years, producing a luminous flare of radiation called a tidal disruption event. These events have been observed in other galaxies, producing flares visible across the universe. In the Milky Way, the rate of tidal disruptions by SAGRA is estimated at roughly 1 per 100,000 years. In 2011, astronomers discovered a compact gas cloud called G2 on a trajectory that would take it very close to SAGRA in 2014. The event was intensely watched. The cloud was partially disrupted by tidal forces as it approached the black hole, producing complex emission features, but no significant brightening of SAGRA was observed. This was in some tension with simple models of what the accretion of cloud material would produce, and subsequent analysis suggested that G2 might be a star with a gas envelope rather than a pure gas cloud. A stellar object would have been less dramatically disrupted by the tidal encounter. We will understand that the galactic center, hidden from optical astronomy by dust and distant from us by 26,000 light-years, is its own separate chapter in the story of the Milky Way's black hole population. It is the place where the predicted dark cusp of tens of thousands of stellar mass black holes may be concentrated around the supermassive black hole, orbiting so densely that mergers between stellar mass black holes and SAGRA minks may occur on timescales accessible to future gravitational wave detectors. The current inventory of confirmed black holes in the Milky Way is the product of roughly 60 years of X-ray astronomy, 10 years of gravitational wave astronomy, and a few years of Gaia astrometry. The total confirmed count is in the dozens. The predicted population is 100 million. Let's talk about how the next decade of observational astronomy might transform that ratio, because several instruments either recently launched, currently operating, or under construction in 2026 are specifically positioned to detect the black holes we have not yet found. Let's talk about what the Gaia mission still has to offer. The European Space Agency's Gaia spacecraft has been releasing its data in incremental catalogues, each one larger and more precise than the last. The discovery of Gaia BH1 and BH2 came from the third data release, published in 2022, but Gaia's mission has not ended. The satellite continues to observe accumulating more observations of each star in its catalogue, and each additional observation improves the precision of the astrometric measurements. The fourth and fifth Gaia data releases, expected in the late 2020s, will incorporate significantly more observations and improved calibration. For the astrometric wobble technique that found BH1 and BH2, more observations translate directly into better sensitivity to smaller wobbles, which means detecting black holes with lower mass companions or at greater distances. Estimates from the Gaia science team suggest that the complete Gaia dataset may yield between dozens and hundreds of dormant black hole systems, with some optimistic projections suggesting the number could be in the thousands. If even 100 new dormant black hole systems are confirmed from the complete Gaia catalogue, it will transform our empirical understanding of the dormant black hole binary population. Those systems can be studied for their mass distributions, orbital properties, companion types, and spatial distribution within the galaxy. They will provide observational anchors for stellar evolution models in a way that the current handful of X-ray binary black holes cannot. Let's talk about the Laser Interferometer Space Antenna, LISA, because it will access a population of merging black holes that ground-based detectors like LIGO cannot reach. LISA is a planned space-based gravitational wave detector, approved by the European Space Agency and expected to launch in the mid-2030s. Unlike LIGO's mile-scale arm lengths, LISA will have arm lengths of 1.5 million miles, with laser links between 3 spacecraft trailing Earth in its orbit around the Sun. This enormous baseline gives LISA sensitivity at much lower frequencies than LIGO, in the range of 0.1 mHz to 1 Hz, rather than LIGO's 10 to 10,000 Hz. At low frequencies, the gravitational wave sources include massive black hole mergers at cosmological distances, which produce signals at millihertz frequencies due to the longer timescales of the mergers. LISA will detect black hole mergers involving masses of thousands to millions of solar masses, the mergers of supermassive and intermediate mass black holes. It will also detect extreme mass ratio in spirals, cases where a stellar mass compact object spirals into a much more massive black hole over thousands of orbits, while LISA observes, providing extraordinarily detailed maps of the space-time near the larger black hole. But LISA will also detect, in the Milky Way and nearby galaxies, a background of individually unresolved compact binary systems. Among these will be many double stellar mass black hole binaries in spiral toward merger. The total number of double stellar mass black hole systems detectable by LISA in the Milky Way is estimated to be in the thousands. While LISA may not be able to resolve individual systems, the aggregate background signal encodes statistical information about the total population. Tonight, we're going to talk about the Square Kilometre Array, because it offers a route to the black hole population through the neutron stars, and specifically through pulsar timing. The SKA telescope array is currently under construction across Australia and South Africa. When complete, it will be the world's largest radio telescope, with a collecting area of approximately 1 square mile of receiving surface assembled from thousands of individual antennas. One of its primary science goals is pulsar timing, the ultra-precise monitoring of the pulses from millisecond pulses to detect gravitational wave signatures. Millisecond pulses are old neutron stars that have been spun up to very rapid rotation rates by accreting material from a companion star. They pulse hundreds of times per second with extraordinary regularity, rivaling atomic clocks in their precision. A network of such pulsars, monitored with sufficient timing precision, constitutes a pulsar timing array that can detect gravitational waves at nanohertz frequencies, far below what LIGO, or even LISA, can access. At nanohertz frequencies, the dominant gravitational wave signal is expected to come from merging pairs of supermassive black holes at the centers of distant galaxies. In 2023, multiple pulsar timing array collaborations, including the NanoGrav collaboration in North America, announced the detection of a background of gravitational waves consistent with what is expected from a cosmic population of merging supermassive black hole binaries. The SKA will significantly improve the sensitivity of pulsar timing arrays, potentially resolving individual supermassive black hole merger systems. But the SKA's pulsar survey capabilities will also dramatically expand the known pulsar population. By finding more neutron star pulsars in the Milky Way, it will better characterize the neutron star population and, by extension, constrain the stellar evolution models that predict the black hole population. The boundary between stellar mass black holes and neutron stars is directly relevant to both populations. No one expects the next decade to yield the complete stellar mass black hole census of the Milky Way. No one predicts that the combination of Gaia, LIGO, Roman, and the SKA will directly detect all 100 million objects. But the number of confirmed black holes should grow from the current dozens to thousands within a decade, and the statistical constraints on the total population will become far more precise. Let's talk about the Roman Space Telescope's microlensing survey, because it is the instrument most directly pointed at the isolated stellar mass black hole population. The Nancy Grace Roman Space Telescope, expected to launch in the mid-2020s, will monitor over 100 million stars toward the galactic bulge for microlensing events in a dedicated survey campaign. Its wide-field infrared camera and space-based vantage point free of atmospheric blurring will allow it to detect fainter and more rapidly evolving microlensing events than any ground-based survey. The Roman microlensing survey is expected to detect roughly 54,000 microlensing events over its lifetime, compared to the thousands detected by OGLE over decades. Of those, an estimated several hundred to several thousand will be caused by stellar remnants, including black holes. The precise astrometric measurements possible from space will allow the nature of the lens to be determined for a significant fraction of these events. If Roman detects 500 black hole microlensing events over its mission, and if those events can be characterized in terms of mass and distance, the result will be the first direct map of the isolated stellar mass black hole population in a region of the galactic disk. It will not cover the full galaxy, but it will provide the first empirical anchor for models that currently rest on theoretical assumptions about kick velocity distributions, binary evolution rates, and stellar mass functions. By the end of tonight, we will understand that the census of black holes in the Milky Way is not static. It is growing, instrument by instrument, survey by survey, and the pace of that growth is about to accelerate significantly. The dark galaxy that runs parallel to the bright one we can see is being mapped, one collapsed remnant at a time. There is a question that naturally arises once you understand that the Milky Way contains 10 to 100 million stellar mass black holes distributed through its disk. The question is, where are they relative to us? How densely are they distributed in our neighborhood of the galaxy? How close is the nearest one we do not know about? Let's work through these numbers carefully, because they are counterintuitive in a specific way. Let's talk about the local density of stellar mass black holes and what it implies. The Milky Way disk has a radius of roughly 50,000 light-years and a scale height, the characteristic thickness within which most of the disk's contents are concentrated, of roughly 1,000 to 2,000 light-years for the thin disk, where most star formation has occurred. The volume of the thin disk is approximately the volume of a cylinder with radius 50,000 light-years and height 2,000 light-years, which is roughly 15 billion cubic light-years. If we distribute 100 million stellar mass black holes uniformly through this volume, the average density is roughly 1 black hole per 150 cubic light-years. A cube 150 cubic light-years in volume has sides about 5.3 light-years long. There are, by this estimate, roughly 1 black hole per 5 light-year cube in the average galactic disk. The nearest confirmed black hole to Earth, Gaia BH2, is approximately 1,200 light-years away. Gaia BH1 is approximately 1,560 light-years away. These are dormant black holes in binary systems, but the model predicts many more isolated black holes at smaller distances, undetectable because they have no companion and produce no detectable radiation. The nearest isolated stellar mass black hole might be significantly closer than White-Swan, 200 light-years. There is no strong reason to expect that the confirmed systems at 1,200 and 1,560 light-years represent the nearest black holes overall. They represent the nearest black holes detectable by current methods. The nearest undetectable isolated black hole, based on the expected local density, could plausibly be within a few hundred light-years. This feels close, but let's talk about what it actually means in terms of physical experience, because a few hundred light-years and dangerous proximity are not the same thing. A stellar mass black hole of 10 solar masses is, by definition, an object with 10 times the mass of the Sun. At a distance of 100 light-years, roughly 600 trillion miles, the gravitational field of a 10 solar mass object is about 10 times the gravitational field of the Sun at that distance. But the gravitational field of the Sun at a 100 light-years is extraordinarily feeble, roughly 100 million times weaker than the Sun's gravity at Earth's distance of 1 astronomical unit. Multiplying by 10 for the black hole's mass gives a force still 10 million times weaker than what holds Earth in its orbit. The nearest stellar mass black hole, even if it were only 50 light-years away, would be completely undetectable by any means available to us except dedicated searches, and would exert no detectable gravitational influence on the solar system. The dramatic properties of black holes, the intense tidal forces, the light bending, the event horizon, only become relevant at distances comparable to the black hole's physical size. For a 10 solar mass black hole, the event horizon is about 30 miles in diameter. The innermost stable circular orbit, where infalling material begins its final plunge, is at about 90 miles from the center. The tidal forces that would be dangerous to a human body reach noticeable levels only at distances of thousands of miles. At planetary system scales, measured in hundreds of millions of miles, a 10 solar mass black hole is gravitationally similar to a 10 solar mass star. It is dark, but not more dangerous than any other object of equivalent mass. Let's talk about the galactic orbit of black holes, because their kinematics add another dimension to where they end up. Stellar mass black holes move through the galaxy on orbits determined by the galactic gravitational potential, modified by any natal kick they received at formation. Black holes with large natal kicks were launched into eccentric orbits at the time of their formation, oscillating up and out of the galactic plane and then back in on timescales of tens to hundreds of millions of years. Black holes with smaller kicks, like those from failed supernovae or from very massive progenitors where the kick is diluted, may remain in roughly circular orbits in the disk. As a result, the local black hole population is a mix of objects with different orbital histories. Some have been in the disk, near the galactic plane for their entire billion-year histories. Others are visitors from more eccentric orbits that are currently crossing through the disk near the Sun. The velocity distribution of the local black hole population is expected to be slightly hotter than the local stellar velocity distribution because of the additional kick velocities at formation. This means that black holes are drifting past the solar neighborhood on timescales of millions of years. The relative velocity between the solar system and nearby black holes is typically in the range of tens of miles per second, set by the combination of the local stellar velocity dispersion and the spread in black hole kick velocities. At these velocities, a black hole would cross the entire diameter of the solar system in a few hundred years, but at the expected local density of 1 per 150 cubic light years, the average time between close encounters, defined as encounters within, say, a few light years, is astronomical. No one expects close encounters with stellar mass black holes to be a meaningful risk on human timescales. No one predicts that the local density of black holes, even at 1 per 150 cubic light years, produces encounter rates relevant to anything we experience or plan for. But the intellectual picture is still striking. There are objects drifting through the space within a few hundred light years of Earth right now, completely invisible to our most powerful telescopes, each one the crushed remnant of a star that burned and died before our solar system formed. The galactic neighborhood is not empty. It is full of dark, dense relics, and we are only now developing the tools to find them. By the end of tonight, we will understand something about the texture of the galaxy that the bright images of spiral arms and glowing nebulae do not convey. The Milky Way is threaded through with the collapsed remnants of its own stellar history. 10 million to 100 million objects, ranging from 3 to 100 solar masses, moving through the same space as the ordinary stars, following the same gravitational orbit, and taking no notice of the fact that nothing about them is detectably visible. The galaxy is older and darker than it looks, and we are only beginning to take its full inventory. When we talk about a black hole, we tend to focus on its mass. Mass is the property that defines how strong its gravitational pull is, how large its event horizon is, and how it interacts with surrounding matter at large distances. But every astrophysical black hole has a second fundamental property: spin. And spin changes nearly everything about what the region near a black hole looks like. Let's talk about what spin means for a black hole and why it matters for the hidden population in the Milky Way. In general relativity, a spinning mass drags the space-time around it into rotation. The faster the spin, the more pronounced the dragging. For ordinary massive objects like Earth and the Sun, this effect, called frame dragging, or the lens-thirring effect, is measurably small. For a rapidly spinning black hole, frame dragging becomes extreme. The space-time near the black hole is pulled into rotation so strongly that, within a region called the ergosphere, nothing can remain stationary relative to distant observers. Everything within the ergosphere is forced to rotate with the black hole, regardless of what forces act upon it. The ergosphere exists outside the event horizon of a spinning black hole. A photon or a particle that enters the ergosphere is carried around by the rotating space-time, but it can still escape. An object that crosses the event horizon cannot. The ergosphere of a maximally spinning black hole extends from the event horizon out to twice the event horizon radius at the equator. The theoretical framework for spinning black holes was developed by New Zealand mathematician Roy Kerr in 1963. The Kerr metric, as the solution to Einstein's field equations for a spinning mass is called, describes the space-time geometry around all astrophysical black holes with any spin rate from 0, the non-spinning Schwarzschild case, to maximum spin, where the event horizon radius equals the inner boundary of the ergosphere. Tonight, we're going to talk about how we measure the spin of real black holes, because spin leaves detectable signatures in the radiation from accreting systems. The material falling onto a black hole in an accretion disk spirals inward in a roughly circular orbit at each radius, losing energy to viscous processes as it moves inward. At some minimum radius, called the innermost stable circular orbit, or ISCO, circular orbits no longer exist, and the material plunges rapidly inward toward the event horizon. The radius of the ISCO depends on the black hole spin. For a non-spinning black hole, the ISCO is at 3 times the event horizon radius. For a maximally spinning black hole where the disk correlates with the spin, the ISCO is at the event horizon itself. For a maximally spinning black hole where the disk counter-rotates against the spin, the ISCO is at 9 times the event horizon radius. Because the material reaches the ISCO and then plunges in, the temperature distribution of the accretion disk is truncated at the ISCO radius. Measuring the temperature and luminosity of the inner disk and comparing to a model of what the disk should look like at different ISCO radii gives an estimate of the ISCO radius and therefore the spin. This technique is called X-ray continuum fitting, and it has been applied to about a dozen black holes in X-ray binary systems. A second technique uses the profile of the iron K-alpha emission line at X-ray energies. Iron in the inner accretion disk is ionized by the intense X-ray radiation and emits a characteristic line at 6.4 keV. As the iron-emitting material orbits at velocities close to a significant fraction of the speed of light near the ISCO, the line is broadened and distorted by special relativistic effects from the high orbital velocity and general relativistic effects from the strong gravity. The shape of the distorted iron line is sensitive to the ISCO radius and therefore to the spin. What these measurements have found is that stellar mass black holes in X-ray binaries span a wide range of spins. The black hole in the X-ray binary, Cygnus X1, has been measured at a spin parameter close to the maximum allowed value, very close to 1 in the dimensionless units used for black hole spin. The black hole in GRS 1915 plus 105, which was for many years the most luminous persistent X-ray binary in the Milky Way, also has a spin close to maximum. Other systems have measured spins closer to the middle of the range. No one expects all stellar mass black holes to have the same spin. No one predicts that the spin distribution of the hidden black hole population would mirror exactly what we see in the small confirmed sample of X-ray binaries. The spin a black hole has when it dies with its massive progenitor depends on how rapidly the progenitor was rotating, how much angular momentum was lost to mass ejection, and how efficiently the collapse conserved angular momentum. Black holes form through different channels: failed supernovae versus ordinary supernovae, first generation versus second generation mergers, are expected to have different spin distributions. Let's talk about the Penrose process, because the spin of a black hole is not just a passive property, it is a reservoir of energy. In 1969, Roger Penrose demonstrated theoretically that energy can be extracted from a rotating black hole through a process involving the ergosphere. If an object falls into the ergosphere and splits into 2 pieces, with one piece falling through the event horizon on a specific trajectory, and the other piece escaping, the escaping piece can carry away more energy than the original falling object had. The extra energy comes from the rotation of the black hole, which is diminished by the process. The Penrose process is not practically achievable by any current technology, but it is believed to be the physical basis of one of the most energetically powerful phenomena in the universe. relativistic jets. When black holes in binary systems or at the centers of galaxies actively accrete material, they often produce jets, narrow beams of high-energy plasma launched perpendicular to the accretion disk and accelerated to close to the speed of light. The energy source for these jets is not well understood in detail, but the Blandford-Znajek mechanism, proposed in 1977, suggests that magnetic fields threading the ergosphere extract rotational energy from the black hole and channel it into the jet. Several of the X-ray binary black holes in the Milky Way produce jets. SS 433 is one of the most dramatic. Two relativistic jets from a black hole accreting at a very high rate, moving at about 26% of the speed of light, have been directly imaged with radio interferometry. The jets precess, tracing a helical pattern in the sky as the black hole wobbles like a spinning top under the gravitational influence of its companion. The isolated black holes scattered through the disk of the Milky Way are not currently producing jets. Without an accretion disk feeding them material and threading them with organized magnetic fields, there is nothing to launch. But if any of those isolated black holes were to encounter a dense molecular cloud, or have a companion star deposited into a nearby orbit by stellar dynamics, the dormant black hole could become briefly active, producing X-ray emission and potentially a jet, before the fuel supply ran out and it returned to darkness. We will understand that the hidden black hole population in the Milky Way is not uniform. It is a population of objects with a range of masses, a range of spins, a range of orbital velocities, and a range of formation histories. The one thing they share is their invisibility, and the spin, which would be among the most observationally distinctive properties of an active black hole, is completely undetectable in the dormant state. The 100 million black holes drift through the galaxy, carrying their spins as an invisible internal property, a history of their formation that we cannot read without finding them first. Let's talk about the event horizon itself, because it is the feature that defines a black hole, and it is far stranger, from a physical standpoint, than most descriptions suggest. The event horizon is not a physical surface. It is a boundary in space-time, the boundary beyond which future world lines, the paths of objects moving forward in time, can no longer escape to the outside universe. Nothing marks it physically. There is no wall, no change in the texture of space, no detectable threshold. If you were to cross the event horizon of a sufficiently large black hole, you would feel nothing at the moment of crossing. The tidal forces, the difference in gravitational pull between your head and your feet, at the horizon of a 10 solar mass black hole would be lethal well before you reach the horizon. But at the horizon of a sufficiently massive black hole, such as Sagittarius A, with its 4 million solar masses, the tidal forces are relatively modest. The horizon radius is proportional to mass, and for a 4 million solar mass black hole, the horizon is roughly 15 million miles in radius. The tidal forces across a human body at that distance from the center would be detectable, but not immediately fatal. You could cross the horizon of a massive enough black hole and not know, from local physical measurements, that you had crossed it. The space-time inside the horizon is not obviously different from the space-time outside it. Light still travels at the speed of light. Objects still fall under the laws of physics, but the geometry has changed in a specific way. The radial direction toward the center has become time-like. Moving toward the center is now moving in the direction of the future, and no more preventable than the passage of time itself. From the moment of horizon crossing, the singularity at the center is not in a particular direction in space. It is in the future. The singularity if general relativity is taken literally without quantum corrections, is a point or ring at which the curvature of space-time becomes infinite. This is widely understood to be a sign that general relativity breaks down at extreme densities, and that a theory of quantum gravity would replace the singularity with something physically meaningful, but currently unknown. The singularity is not the destination you fall toward in any direct experiential sense. It is the theoretical endpoint of a trajectory that the physics as we know it cannot describe past a certain point. What an infalling observer would experience from their own perspective is a finite time from horizon crossing to reaching the singularity. For a stellar mass black hole, this proper time is measured in fractions of a second. For a supermassive black hole like Sagittarius A, it is measured in hours, giving a hypothetical infalling observer time to observe the accumulating light from the entire future of the outside universe, blue shifted and accelerated by the extreme space-time curvature, before reaching the singularity. But an outside observer watching someone fall into a black hole would see something entirely different. The infalling person would appear to slow down as they approach the event horizon, their movements becoming more and more sluggish, their light becoming more and more red-shifted. They would appear to freeze at the horizon, becoming infinitely dim and infinitely red-shifted, and effectively vanishing from the outside observer's view. The two descriptions, one from inside and one from outside, are both correct and both complete descriptions of what happens in their respective reference frames. This is not a paradox. It is a consequence of the geometry of space-time near a black hole, a geometry in which simultaneity is relative in an extreme way. The 10 to 100 million stellar mass black holes in the Milky Way each have an event horizon of this nature, a boundary in space-time hidden inside a sphere between 30 and 600 miles in diameter. The rest of the universe around each horizon goes on as normal. Stars orbit, gas drifts, cosmic rays pass through, and the event horizon sits at the center of the local space-time, silent, perfectly dark, and carrying inside it, in the frozen light of everything that ever fell through, a record of every object that ended its journey there since the black hole formed. We cannot read that record. We cannot even send a probe to look, because anything sent through the horizon cannot send information back out. The interior of every black hole in the Milky Way is causally disconnected from us, permanently and completely. What is inside, and what is outside, and the horizon between them is the sharpest boundary in the known universe. We have spent tonight talking about black holes as if they are permanent. In the context of human timescales, they effectively are. In the context of the age of the universe, they are nearly permanent. But the physics of quantum mechanics applied to the vicinity of a black hole event horizon predicts that they are not permanent at all. They simply evaporate on a timescale so long that it dwarfs every other timescale we discuss in astrophysics. Tonight, we're going to talk about Hawking radiation and the ultimate fate of the black holes hiding in the Milky Way. Because what happens to them in the deep future is the final chapter of their story. Let's talk about what Hawking radiation is and how Stephen Hawking came to discover it in 1974. In classical general relativity, nothing escapes from a black hole once it has crossed the event horizon. The event horizon is by definition the boundary beyond which the escape velocity exceeds the speed of light. But quantum mechanics complicates this picture. In quantum field theory, the vacuum is not empty. It is filled with pairs of particles and antiparticles that pop into existence for brief moments, borrowing energy from the uncertainty principle, and then annihilate before the borrowed energy must be repaid. These are called virtual particle pairs. Near the event horizon of a black hole, Hawking showed that this process takes on a special character. Sometimes a virtual particle pair forms very close to the horizon, and the negative energy partner falls inward, while the positive energy partner escapes outward. The escaping particle carries positive energy away from the black hole. Over time, this process removes energy from the black hole, and since mass and energy are equivalent in relativity, the black hole loses mass. It slowly evaporates. The radiation emitted by this process, called Hawking radiation, has a thermal spectrum. The temperature of the radiation is inversely proportional to the mass of the black hole. A more massive black hole is colder. A smaller black hole is hotter. For a stellar mass black hole of 10 solar masses, the Hawking temperature is approximately 6 times 10 to the power of -9 Kelvin, billions of times colder than the cosmic microwave background, which is still at approximately 2.7 Kelvin today. This means that a stellar mass black hole is receiving far more energy from the cosmic microwave background radiation that bathes the universe than it is losing to Hawking radiation. It is effectively growing very slightly, not shrinking. In the current epoch of the universe, all stellar mass black holes are gaining mass from the cosmic microwave background faster than they lose it through Hawking radiation. They are not currently evaporating. They will not begin net evaporation until the universe has expanded and cooled to the point where the cosmic microwave background temperature drops below the Hawking temperature of the black hole. For a stellar mass black hole, this will not occur until the universe is roughly 10 to the power of 15 times its current age, an incomprehensibly remote future. Once net evaporation begins, the timescale to complete evaporation depends on the initial mass of the black hole. The evaporation timescales as the cube of the initial mass. For a black hole of 10 solar masses, the evaporation time is approximately 2 times 10 to the power of 67 years. To put this in perspective, the current age of the universe is roughly 13.8 billion years, or about 1.38 times 10 to the power of 10 years. The evaporation time for a stellar mass black hole is roughly 10 to the power of 57 times the current age of the universe. No one expects the future timescales relevant to black hole evaporation to be intuitively graspable. No one predicts that the human mind, adapted to timescales of years and generations, would find it easy to hold in mind the difference between 10 to the power of 10 and 10 to the power of 67. Absolutely no one anticipates, when first learning about Hawking radiation, that the process is so slow for astrophysically relevant black holes that they are effectively permanent on any timescale a civilization might care about. Let's talk about what the universe looks like during and after the epoch of black hole evaporation, because it is a remarkable extrapolation of known physics into a future almost entirely unlike the present. By the time the last stars in the Milky Way burn out, roughly 10 to the power of 14 years from now, the stellar mass black holes scattered through the galaxy will have barely changed. Their masses will be unchanged. The galaxy around them will have darkened. The star-forming gas will have been exhausted. The last red dwarfs, the smallest and longest-lived stars, will be cooling to black dwarfs. The white dwarfs from earlier generations of stars will have cooled and crystallized. The neutron stars will be cold and dark. The galaxy will be a dim collection of cold compact objects and black holes orbiting each other in an otherwise empty space. For the next several trillion years after that, the black holes are the dominant features of the galactic remnant. The other compact objects, white dwarfs and neutron stars and cold planetary remnants will gradually be ejected from the galaxy by gravitational scattering interactions or fall into the black holes. The galaxy effectively becomes a slowly emptying collection of black holes. And then, beginning at timescales of roughly 10 to the power of 67 years, the stellar mass black holes begin to show measurable mass loss from Hawking radiation. As each black hole loses mass, its temperature increases. As the temperature increases, the radiation rate accelerates. The last moments of a black hole's life are increasingly rapid, culminating in a final burst of Hawking radiation when the remaining mass is of the order of the Planck mass. What happens at that final moment is not known. The physics at Planck densities and temperatures is beyond the reach of quantum field theory in curved space-time, which is the framework in which Hawking radiation is derived. A theory of quantum gravity, combining general relativity and quantum mechanics in a consistent way, would be needed to describe the final instant of a black hole's life. We do not have that theory. Let's talk about why the Hawking radiation calculation was so significant beyond its astronomical implications. The original derivation by Hawking in 1974 revealed a tension at the heart of physics that has not been fully resolved in the half-century since. In quantum mechanics, information cannot be destroyed. Physical processes are time-reversible in principle, and the state of a system at any moment in principle encodes all information about its past. In classical general relativity, anything that falls into a black hole is permanently lost to external observers. Its information is hidden behind the horizon. Hawking showed that the radiation emitted during evaporation is thermal, meaning it is random, carrying no information about what fell in. If Hawking's calculation is exactly correct, the information about everything that ever fell into the black hole is destroyed when the black hole evaporates. This contradicts the quantum mechanical principle of unitarity, the conservation of information. The tension between these two frameworks is called the black hole information paradox, and it remains one of the deepest unsolved problems in theoretical physics. Proposed resolutions range from the idea that information escapes in subtle correlations within the Hawking radiation that are not apparent in the thermal approximation, to the idea that black holes leave Planck scale remnants after evaporation that store the information, to the idea that space-time itself must be modified at a fundamental level to resolve the paradox. The most discussed recent approach, developed through the work of many physicists including Pennington, Almhiri, and others in the 2019 Island Rule Papers, suggests that information does escape during evaporation, but through a mechanism involving subtle quantum correlations between the radiation and the interior of the black hole, accessible only through a calculation that requires quantum gravity. The information paradox is not an astronomical problem. It will not affect observations of black holes on any timescale, but it reveals that the 100 million black holes drifting through the Milky Way are not merely collapsed stars. They are sites where two of the most successful theories in the history of physics, quantum mechanics, and general relativity are in genuine conflict with each other. The resolution of that conflict will require new physics, and that new physics, whatever it is, may ultimately change our understanding of the nature of space-time itself. By the end of tonight, we will understand that the hidden black holes of the Milky Way carry their mysteries at multiple levels. They are dark, they are numerous, they are scattered through the same space we inhabit. They carry in their spins and masses the records of their stellar progenitors, and they carry in their evaporation timescales a far future endpoint that overlaps with the deepest unresolved questions in physics. They are not just compact objects. They are the places where our understanding of nature is incomplete. We began tonight with a gap between two numbers. 100 million, the estimated number of stellar mass black holes in the Milky Way, and a few dozen, the number we have confirmed. The gap is not a failure. It is the honest situation of a civilization that has only recently developed the tools to look for dark objects. The confirmation of Cygnus X1 as a black hole in the 1970s was not the beginning of black hole astronomy. It was the confirmation of a concept that general relativity had predicted in 1916, and the first detection of gravitational waves from a merging black hole pair in 2015 was not the beginning of gravitational wave astronomy. It was the culmination of decades of engineering and theoretical work. The tools we have to count the dark population of the Milky Way are young tools. They have been productive for only a few years. We should not expect them to have resolved, in a few years, a census problem that will take decades. That gap between what the physics requires and what our instruments have actually found is not a failure of astronomy. It is the accurate picture of where we are. We are at the beginning of the era in which we are learning to count what is dark. The tools to do it, Gaia's astrometry, LIGO's gravitational wave detectors, the coming Roman Space Telescope's microlensing survey, are either just beginning to produce results or will be producing them within a decade. The Milky Way we live in is not the Milky Way we thought we lived in. When we look at images of the galaxy taken in visible light, we see the bright spiral arms, the hot blue stars of the disk, the warm yellow bulge at the center. It is beautiful and familiar, and approximately 300 billion solar masses in total, but distributed through that same structure, following the same gravitational potential, orbiting through the same spiral arms on timescales of hundreds of millions of years, are between 10 and 100 million stellar mass black holes, most of them isolated, none of them emitting any light. Each of them the collapsed remnant of a massive star that lived and died before the sun was born. They are here, right now, in the space between the visible stars. The nearest confirmed black hole is 1,200 light-years away. The nearest unconfirmed and likely undetected black holes may be far closer. The density of stellar mass black holes in the disk of the galaxy is estimated at roughly 1 per 100 to 200 cubic light-years in the neighborhood of the Sun. That means within a sphere, 100 light-years in radius around our solar system, there are probably several dozen black holes. They are not threatening. A black hole 30 miles in diameter exerts no more gravity at a distance of several light-years than a star of equivalent mass. Proximity is not danger at the distances we are talking about. The nearest stellar mass black hole could be within 10 light-years of us, and we would not feel any tidal effect different from the ordinary gravitational field of the galactic disk. But they are remarkable as objects. Each one is a place where space-time has ended, a hole in the fabric of the universe sealed by its own gravity, holding mass without taking up any meaningful space, warping the paths of light that come too close, and then simply waiting. They do not age in any meaningful sense. They do not burn out. They will outlast the galaxy that made them. In the far future, when the last stars have died, when the gas in the disk has been exhausted, when the Milky Way and Andromeda have merged into an elliptical galaxy, and the stellar population has declined to red dwarfs and their cooling remnants, the black holes will still be there. They will persist on timescales that require scientific notation to express. A stellar mass black hole evaporates through Hawking radiation, a process so slow that the timescale is approximately 10 to the power of 67 years. The current age of the universe is roughly 10 to the power of 10 years. The black holes formed in the first billion years after the Big Bang have lost a fraction of their mass so small it cannot be meaningfully compared to their original mass. They are, for all practical purposes, permanent. Remember that the number of confirmed black holes in the Milky Way will increase dramatically within the next decade as new surveys and instruments come online. The Gaia mission, the Roman Space Telescope, and the continued operation of LIGO and its growing network of international partners are each independently approaching the problem from a different direction, and each of them is finding things the others cannot reach. Remember that Gaia BH1 and BH2, found by watching stars wobble, are almost certainly the first confirmed members of a population of thousands of similar systems within range of Gaia's sensitivity. And remember that the galaxy we live in, the one we call home, is darker and more complex and more densely populated with the remnants of ancient stellar lives than any image of its bright surface suggests. We are grateful you spent tonight with us in the dark. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of our galaxy together. Good night.